Okay, so we have discussed differentiating and integrating, all right, the natural e to the x function, all right, the next natural exponential function. Now what we're going to do is talk about how do I integrate or differentiate all the other types of exponential functions, something that has a base other than e. Now the good news is, all right, we're going to use some of the things that we have discussed with y equals e to the x to develop our rules, all right, for the derivative of all other exponential functions. Now, so to get to the development of this, what we're going to use is this, once again, this idea, and I think I mentioned this in the last video, that because e and natural log are inverses, that we can rewrite things, all right, in equivalent form. So if you look at what we have, all right, with this first line here, we have y equals e to the x. Well, I can rewrite this as e to the natural log of a to the x, because once again, e and natural log are inverses of one another, all right, so this is really just one. All right, but by doing this, it allows me then to pull this x out front because I can apply my property of natural logs, all right, to this piece right here. So I end up with this. And the reason why we'd want to do this is because we have a rule for the derivative of e to the x. So by rewriting it this way, all right, we can reuse, all right, one of the rules that we've already talked about. So we can go from here to here, all right, and they're equivalent forms, but then I can take the derivative of this piece, all right, which we already have a rule for to develop our new rule. So if we look at, all right, the next piece here, all right, maybe, all right, here we go. All right, so, all right, I think I have a lot of these open all of a sudden. So let's see, how do I get rid of that? Well, let's get rid of that one. Sorry about that. That's not what I want at all. All right, so I was trying to use my screen shade here, but maybe, there we go. All right, so let's try this again. All right, so the derivative of y equals a to the x. So see, technical difficulties whether I'm there or not. All right, so, okay, so now, so notice this is just what we talked about. So we're going to take our exponential a to the x, and we're just going to work with it in this form since we already have a rule for the derivative of e to the x. All right, so that's what we're going to look at. And we're going to take the derivative of this guy. All right, so the derivative of e to the x natural log of a, all right, and when we do that, we know, okay, we know the derivative of e to the x is e to the x, so that's all of our e to the x there, so e to the u, and then e to the u, and then the derivative of e to the u. Now, what's the derivative of u? Now, if we just have to remember that natural log of a is a constant, so this is really something just like 2x or 3x or negative 5x, right? So natural log of a, x, all right, or x natural log of a, the derivative of that is just this constant natural log of a. Now, once we do that, we can go ahead and just rewrite this and know that, okay, I can put the x back, e and natural log undo each other, and so I end up with just that piece right here. So our derivative, all right, of any exponential function is just going to be natural log of a times that exponential function. Now notice how this still works and it still follows our rules, all right, for what we have done, because now notice if I did, okay, well what about this guy, right? We already have a rule for this, right? So notice y prime would be the natural log of e times e to the x, and the natural log of e is 1. All right, so it still fits the rule we have developed for all right, exponential functions. All right, now once again, don't forget to chain it. So if we have a to the u, okay, so you're going to have the natural log of a out front because that's the part of the definition of the derivative of our exponential function. But then we also have to multiply by our du dx piece. All right, so let's take a look at some examples. All right, so all right, the first one here we all should know already. So once again, and just like I said, you know, you can just go right to e to the x, or all right, you can say that, well, okay, that would have been natural log of e times e to the x, which once again would have given us e to the x. All right, so the derivative, all right, with respect to x of 8 to the x would be natural log of 8, and remember that's just a constant, times our exponential. All right, 8 to the x. So then the derivative of this guy, okay, so derivative of 5 to the u, all right, so this is our u this time, would be the natural log of the base, so natural log of 5, times a to the u, which is this guy, and then times du dx, and the derivative of 7x is 7. And if you clean that up, you can write it as 7 natural log of 5 times 5 to the 7x, and that would be your derivative. All right, so let's look at a few more exercises and examples that are just a slightly bit more complicated, all right, but still follow our rules here. So if we look at this guy, All right, so I'm taking the derivative of this. Notice this is still 7 to the u. All right, so 7 to the u. So when I take the derivative of this, it's still going to be the natural log of 7 times 7 to the u, which is all of this stuff, but then times the derivative of u. All right, so then derivative of 6x is 6. The derivative of negative sine x is going to be negative cosine x. All right, so you can leave it like this. You can move it around however you like. So natural log of 7, that doesn't look really good. I don't know what that is. So let's do this again. Natural log, there we go, that's a little bit better. 7 times 6 minus cosine x times 7 to the 6x minus sine x, all of that up there. So, all right, so you can rewrite it if you want. All right, so now let's look at, our next problem here, and I'm missing a parenthesis, it looks like. So let's add that guy on right there. So we want to take the derivative of this entire expression. All right, so once again, we're going to apply the rule that's appropriate to each piece. So the derivative of natural log of u, is 1 over u, so that would be sine x. And then the derivative of u would be cosine x. And then I'm going to come to the next piece. So the derivative of a to the u would be the natural log of a, so natural log of 8, times a to the u, or 8 to the tangent x, and then times the derivative of u, and the derivative of tangent is secant squared x. Now you would probably see this written as, cotangent x, and then plus natural log of 8, secant, I'm kind of getting slow here, secant squared x, and then 8 tangent x. All right, so you can see that we just kind of keep adding rules, okay? All right, so the part of this is that you just have to be familiar with each piece and then what rule applies. So we've added 3 or 4 new rules in the last couple of lessons. All right, now we're going to talk about this because we have rules for taking something to a power if the power is a constant. But what do we do when we have a function to a function, or a function raised to a power that is also a function? And I'm going to show you 2 different ways to approach the problem. Now, once again, it's your choice on how you do this, all right, but you do need to be proficient with one of the methods. All right, so the first one that I'm going to discuss is what we've done before, all right? So it's a lot like our logarithmic differentiation. We're just going to take the natural log of both sides of this problem. So the first thing I'm going to do is this guy. And the reason I'm going to do this is because we want to get this function out of the power. And once I take the natural log of both sides, I can now move this guy out front using those properties of natural log. So I get the natural log of y equals x squared times the natural log of 2x. Now, so once I get to this, all right, now this is really all rules that we know or should know and be able to apply. So I'm going to start with the left side here. So the natural log of y, okay, so the derivative of natural log of u is 1 over u. So that's going to be 1 over y times the derivative of u, the derivative of y in this case, which is y prime. Now, when we come over here, we have a product. So the product rule is our major rule. So the derivative of the first, 2x, times the second, plus the first times the derivative of the second. Now, when we do this, we have to follow our rules for the derivative of natural log. So derivative of natural log of u is 1 over u times dux, which is 2. So then if we clean this up, y prime equals, I'm going to cross multiply and multiply by y, and that's 2x, natural log of 2x, and then the 2's are 1 here, we get to cancel with an x here, and then plus x here. And then once again, we know what y is from above. So y is 2x to the x squared power, and then times 2x, natural log of 2x, plus x. All right, so that's one way of doing the problem, and it's just like we did with logarithmic differentiation. Take the natural log of both sides, use your power property to pull that guy out front, and then follow your rules. Now, the other way is to kind of stay within, all right, this is an exponential, so we could rewrite it a little bit of a different way. So, and that goes back to writing it like we develop our rule for all other exponential functions. So I'm going to rewrite this using this e to the natural log of 2x to the x squared. All right, so once again, this is really just 1. All right, so I haven't done or changed my equation. It's still equivalent, all right, as long as I multiply by 1. Now, once again, I'm still using this same power property here, but now it's in the form, all right, of an exponent, all right, since we're in an exponent problem now with e to the x here. So I'd have this guy. Yeah, there we go. All right, so now, once I get it to this, I have a rule for the derivative of e to the x. And my rule, all right, for the derivative of e to the u is e to the u, so it's going to be e to all this stuff, times derivative of u, which, notice, I'm going to take the derivative of this guy, which is the exact same product we have right here. All right, so I know that that's going to be 2x natural log of 2x plus x. All right, I'm just going to kind of, to speed this up, just reuse what we know. So notice the product we have here is the exact same product we have here. Now, once again, I can go back and rewrite this. This is e to the natural log of 2x to the x squared, and then times all this stuff. And then once again, we know this is 1. They undo each other, so I'm really left with what I started with, which is this whole 2x to the x squared, and then times 2x natural log of 2x. That's really bad. Let me erase that. 2x and natural log of 2x plus x. There we go. So you can see that we get the same answer. So once again, it's kind of your preference, all right, on which way you would like. So if you want to be consistent and then just keep doing logarithmic differentiation for all these, that would be perfectly fine. All right, so at this time, all right, so why don't you try this one, all right, and see how you do, all right, and so pause the video and then turn it back on and we'll work through the problem together. Okay, so here we go. I'm going to go ahead and do this with logarithmic differentiation. So I'm going to take the natural log of both sides. All right, then I'm going to move the power out front. All right, and now I can take the derivative. So the derivative on the left side would be this guy. Using our product rule over here, it's going to be 3 times the natural log of sine x plus 3x times cosine x over sine x here. All right, and so to finish the problem, this will be y prime equals y, and I'm going to go ahead and put this in, and then times all of this. So 3 natural log of sine x plus 3x. So once again, you're probably going to see this written as cotangent x like this. All right, so that's the answer that you should have come up with. All right, so let's now shift gears a little bit and talk about integrating our exponentials. All right, and the one thing that we have to do here, all right, is make sure we account for the natural log part. So if, notice we know when we take the derivative, normally we have the natural log of the base out front, so if that constant isn't there, okay, it must have canceled out. So when we reverse the process, we're going to have to divide by the natural log of a, and opposite of when we take a derivative and we multiply by that. So let's take a look at an example here. All right, so if we want to integrate, all right, this guy, all right, so I'm going to integrate it, and I get the same exponential, so that's going to be 5x. And I divide by the natural log of that base, and then we have our plus c, all right, since we are in an indefinite integral here. Now, once again, the good news is I could, take the derivative of this, and then I should get back to what our integrand was, all right, when we started the problem. All right, so now let's look at this guy. Now, notice it's 2 to the 5x, so you could do a quick u substitution here. Let u be 5x, and then du would be 5 dx. And once again, we just want dx, so we're going to divide by 5 on both sides. So 1/5 du equals dx. And now we can substitute all that. So we'd have 1/5 the integral of 2 to the u du. All right, and then when we integrate that, we have 1/5 the integral of 2 to the u would be 2 to the u over natural log of 2, and then plus c. And then once again, if we're doing an indefinite integral, we want to go back and put this in terms of x. So 2 to the 5x, and then I'm just going to multiply our two constants here, so 5 natural log of 2 plus c. All right, so that's how we do those types of problems. All right, so let me give you an example to do on your own here. All right, so if you would go ahead and do this first problem, all right, on your own, go ahead and go through the problem, solve it, and then turn the video back on, and I'll work through it too. All right, so let's see how you did. All right, so in this case, once again, when we have an exponential and we're integrating, all right, typically the exponent is going to be your u. So notice that there are kind of some telltale signs when we start looking at the integrand. Oh, it's an exponential. My u is probably going to be, all right, the exponent or the exponential itself. All right, so in this case, I would just let u be tangent x. That means du is going to be secant squared x dx, so we get a direct match. So I just end up with the integral of 4 to the u du. My u's and my 4's look awful and all like there. All right, so the integral of that's going to be 4 to the u over the natural log of 4 plus c. All right, and then once again, if we go back to terms of x, so 4 tangent x over the natural log of 4 and then plus c. All right, so one final example. All right, so I want to give you at least one definite integral here for you to try and attempt. All right, so go ahead and pause the video, all right, and see how you do on this guy, and then I'll come back and work it for you. All right, so let's jump right on in here. So once again, we really have two choices on our u here, either the exponent here or the denominator. All right, but I'm going to go with the exponent here. So u is equal to the square root of x, which means du is equal to 1 over 2 square root of x dx. So almost an exact match up here. So all I need to do is multiply by 2, all right, to get an exact match for our substitution. So now our integrand is going to be 6u du. I'm going to move my 2 out front. Now my integrand is in terms of u, so now I want my limits of integration to also be in terms of u. So now I'm going to plug x in here. So the square root of 1 is 1, so my lower limit of integration is 1. Then I'm going to plug 4 in here. Square root of 4 is 2, and so that's my upper limit of integration. All right, so now when I integrate, I'm going to leave the 2 out front. All right, the integral of 6 to the u would be 6 to the u divided by the natural log of 6. All right, I'm going to evaluate from 1 to 2. Scroll down just a little bit here. All right, so now I'm going to have 2, and then I'll have 6 squared, which is 36 over the natural log of 6, minus 6 over the natural log of 6. All right, and so then if I do that, 36 over natural log of 6 minus 6 over natural log of 6 would just be 2 times 30 over the natural log of 6. All right, and then if you just multiply that out, you could end your answer right there. Nice exact answer. All right, so that's going to wrap up our lesson on integrating and differentiating other exponents. So go ahead and try the homework. And remember, I'll be back in class on Wednesday. So hopefully by the time I get back in class, you've finished section 5.4 and 5.5, and you have all those questions ready to go.